Hello everybody, welcome to another video lesson. Today we're going over vectors in the coordinate plane. Our objective for this video is to represent and operate with vectors in the coordinate plane. So let's get right into our concepts. Okay, first question I want to ask is how accurate were our measurements in previous lessons? When we would look at the magnitude of a vector, we would have to bring out our ruler and see how many centimeters it was, or inches, or whatever. And there's often error in our measurements there. But what we can do is we can have these vectors kind of imposed in the coordinate plane, okay, like vector OP here. Okay? And we can see here that the terminal point, as long as our initial point is on the origin, okay, then our terminal point is going to have some x value and some y value, right? Some x value and some y value, just like any point would on the coordinate plane, okay? So the coordinates for P would be xy. Now we can actually represent these coordinates, okay, in what we call component form for our vectors, okay? And we denote it like so. Okay, so they look like an ordered pair, right? But instead of our brackets, we have these kind of more arrow-like brackets here, okay? Okay, so that is if we have a vector that starts on the origin, okay? But if you have some other vector, just some general vector that is not on the origin with its initial point, all right? Then that distance, okay, between your x1 and x2, right? So the difference between x1 and x2, okay, that's going to be the first component for your component form. And then the distance from y1 to y2, right? So the difference between y2 and y1, that's going to be the second component for my component form. Okay, so it's just this distance here, right, in more general terms, and this distance here, again, in more general terms, just going from y1. So if I were to draw my triangle here, we would have this distance here and this distance here, just like we had over here. Okay, but now I've got x2 minus x1, 1 here, and I've got y2 minus y1 as my distances there. All right. So that is component form. Okay, what about the magnitude when we have a vector in component form? Well, remember we've got our x components and y components here. Okay, so I've got x2 minus x1, y2 minus y1. All right, now what we really have here every time we set it up like this is going to be a right triangle, right? So if I were to set up a generic triangle like this off to the side here with leg x and y, and then our hypotenuse is AB, okay, to find that hypotenuse, right, that would just be x squared plus y squared, right? One leg squared plus the other leg squared equals our hypotenuse squared, okay? And then we can solve for AB, just like so. So with that in mind, okay, it's sort of a play on our Pythagorean theorem and our distance formula. The magnitude of vector AB is going to be equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, again, just looking at our Pythagorean theorem here. Make sure you get that written down, and we'll take a look at operations. Okay, when we have a vector in component form, like a and b here, and say k is a scalar, so k is just some number, right? Some number with a certain magnitude. Then when we add our vectors, all right, this makes it a lot easier for us. Now we don't have to go tip to tail or tail to tail and draw anew our resultant vector. We can immediately find what the sum of these vectors is by just adding the first component, so a1 plus b1, and then adding the second component, a2 plus b2. And that's going to be our resultant vector there. And same with subtraction. And if I have a scalar multiple, all right, so k times a, I can just think of it kind of as distributing that to each one of my coordinates. So I'll have k times a1 and k times a2, okay? That's it for our concepts. Let's get into some examples here. All right, I've got, we're trying to find the component form of a b with our given initial terms. So this a is going to be my going to be my initial point, and B is going to be my terminal point, right? So our sort of formula here for finding our coordinate or finding our component form is going to be x2 minus x1, y2 minus y1. So let's see, A is going to be x1 and y1, and B is going to have our x2 and y2. Okay, so we can just plug these right in and calculate. So that'll be 6 minus negative 2, and then 1 minus negative 7 from A. Okay, so it's just the components from A subtracting the the components from B subtracting the components of A. All right, and then you solve that, you get 8, 8, which is going to be our component form. So use that logic and see if you can find the component form for the example on the right. Okay, hopefully you got -9, -11, and we can move on to magnitude. All right, finding magnitude for AB with the given initial term. So we have the same vectors here, A and B, and we're just going to find the magnitude of each one of them. So again, our formula looks like this. We've got our distance in the x squared plus our distance in the y squared. So I would just go ahead again. I've got x2, y2 for my B coordinates, and x1, y1 for my A coordinates. So all I got to do is plug those in. Okay, so I'll have 6 minus -2 quantity squared plus 1 minus -7 quantity squared. That's going to give me 64 plus 64. Take the square root of that, and that gives me square root of 180, or approximately 11.3. Okay, so using that logic, go ahead and try to figure out, pause the video, try to figure out the magnitude of AB on the right-hand side. Okay, this is what I got here. Now notice we already found the component form for AB, right? We already found that component form. And so when that is the case, this is going to be A1 and A2, right? And so when we have that, we can just plug in A1. So it'll be A1 squared plus A2 squared in this formula here. So this would be my A1 and A2 squared. So I don't have to go ahead and recalculate because I already did this x2 minus x1 and y2 minus y1. So I don't need to recalculate that. I'm going to get the same answers here. I'm going to get -9 squared and -11 squared if I go ahead and plug that directly in. Okay, so just keep that in mind. Hopefully you got square root of 202. Okay, looking at operations here, we're going to take a look at these operations here with vectors A, B, and C. Notice A, B, and C are given to us in component form. Okay, component form. So for this one on the left, this first thing we're going to do, we're going to multiply this scalar of 4 with A. Okay, and if you remember, if A has components A1, A2, and we multiply that by a scalar, that's just going to be that scalar times A1, and then that scalar times A2, right? So 4A is going to be 4 times -4, that's our component here, and then 4 times 1, which is our component here. That's going to give us a -16, 4 for our components of 4A. And then let's see if I've got A plus B. Again, we're just adding the components, the first components of A and B. And then for our second component, we are adding the second components of A and B, right? So let's see, 4A plus C, I already have the components for 4A here. So that'll just be 16 plus -3, getting that from up here, and 4 plus 0, again, 0 is coming from C here, right? So that's going to be -19, 4. All right, so use that and see if you can find the solution for 2A plus 4B minus C. Go ahead and pause the video, see what you get. Okay, this is what I got here, 322. All right. Yeah, just going step by step, going from left to right, multiplying your scalars, and then when you get to C, again, we don't have to think about adding the, subtract the components for C now. Instead of adding them, we would just subtract them. We don't have to think like we used to with adding the opposite when we were doing tip to tail or tail to tail. Okay, so that is all that we have for today, guys. Good luck with your practice.